There's a lot to talk about, so I'm going to be bouncing around different topics, different things as they come to mind. I'm just going to freely talk as I walk here. So without getting into the history of how we became the axiom of it's a DNA, it's a gene problem, right? So let me just ask you a question for you to reflect on. If breast cancer ran in your family, how come, say your mom had breast cancer like my mom? I mean, yeah, there's risks associated with my sister and perhaps me being a male, but did her mom have breast cancer? 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 And did her mom have breast cancer? So you gotta start looking at things like that and questioning the fact that when you consider things that run in your family, when you look at the hard data, about 5% of cancers, some say as many as 8, maybe 10%, run in the family. But what I can say for sure runs in the family is the food you share and the lifestyle that you have. So when you look at things like cancer, it's very, very easy to go ahead and assume that, these things run in my family, because that's what we're told. So let me tell you a story. My mom had breast cancer. She got diagnosed when I was 6 months old. That's what led me onto this whole journey, is when I started getting into modern healthcare as we know it. You look at things, and I realized very, very quickly that cancer and things that we learn in school is very much different than the natural half. And there are these two paths, these two parallel tracks of health, and they never intersect. And so you got to start looking at that and seeing where they may or may not cross paths. So I'm going to pull over here real quick so I can focus on you guys for a moment. So basically, when we look at things as a genetic standpoint, when you look at the science behind it, when they started testing the genome theory, right, that was a huge thing. I mean, the government spent so much money, so much money on mapping out the human genome. When they looked at, first we studied a worm. We saw that, a worm had, I think, 18, maybe 20,000 different genes. They said, wow, there's 20,000 genes in a worm. The human must have 150,000 genes. And then we slowly discovered, as we're mapping out the human genome, that we also have only 20,000 genes. So it was a huge shock to, humans, and we're like, wow, we have as many genes as a worm. So always be critical and always be thinking. You know what I mean? Science should never be hard. People say, I believe in science, and that's great, but you should always be questioning things. Chemotherapy, radiation, and surgery, those are the only 3 things we can legally give you in America as a breast cancer, as a cancer patient. So when you start pondering these things and realizing that maybe, just maybe, it was a lifestyle, maybe it was a nutrition deficiency. We know that many things cause cancer. We know viruses cause cancer. So is there a one-size-fit-all for treating these things? Probably not. So the future of medicine is the right medication for the right person at the right time. Could this mean chemotherapy? Perhaps. Drug companies aren't going to admit that there's really beneficial effects without the side effects to chemotherapy at about 5% of the dose. But when you're getting charged $8,000 to $10,000 a month for chemotherapy, are you really going to have that conversation that, you could have a profound effect on your cancer cells, because we know it kills cancer cells. You don't have to be smart or dumb to know that. Chemotherapy works in a sense. I'm not going to go down that rabbit hole quite yet with you. But when you look at things like that, would you ever consider the fact that you can use chemotherapy at 5% of the dose if the companies are going to only be making 5% of the profit? So again, follow the money. So again, when we start looking at the DNA expressions and seeing that and starting to map out the genome, all the genes in the human body, I'm coming back to that topic, and you start looking at that and they were like, oh my God. So they started comparing different types of cancer to mapping out, once that human genome was completely mapped out. Going the wrong way here. They looked at it and they said, okay, we've mapped out the human genome. Project is done. Then the huge light bulb went off of, well, let's start mapping out cancer genes, and let's start seeing if we can see specific oncogenes. Oncogenes are genes that are turned on that produce cancer. Okay. So let's talk about that for a minute. When you look at oncogenes specifically, in certain types of cancer, that was the goal, is let's map out these oncogenes and see the trends, because if we can map out the whole human DNA genome, why can't we map out certain types of cancers and see what types of genomes or what types of genes and genetic expressions are turned on with this. So I need to sit down for this part because this is where it gets fun for me. So here's what we know today. If you took all these different, I think they started with lung cancer and they started with colon cancer, and they said, okay, we should be able to know that there is all these certain types of genes that we realize are expressed in cancer. The biggest one that's in over 50% of the cancer is called the P53 gene. So they looked at that and said, okay, we should be able to take that P53 gene, say that's one gene, and look at all these other ones, and they should be very common in between every cancer patient, right? And we know now that it's not at all. And it is a term that is called heterogeneity, oncogenetic you know what I'm saying. Heterogeneity, meaning that there's a difference or indifference in the genes in between cancer patients. So let me put it like this in super, super simple English. You have colon cancer. Colon cancer should express genes X, Y, and G, or as X, Y, and Z in cancer. So you should be able to take those X, Y, and Z genes and pull them, all the different tissue and cancer slices from colon cancer, and no matter who you take it from, and they should all be the same. They should always express X, Y, and G. Well, they're taking all these slices and all these different tissue samples, and they're saying, well, there's X shared between them, but you're getting G, you're getting gene A, you're getting gene N that's turned on in this patient, but you're getting X, Y, and Z in the other patient, and then you're getting maybe only Z in the third patient. So there's this huge variability, you know what I mean? Meaning 100% of them, if they were all X, Y, and Z, it'd be 100%, meaning that you could probably say that it's a genetic expression problem. But when all these different patients are having different expressions of gene, it's completely random. It's completely random. So that's what I'm getting at. Hope you're following with me this much. So what I wanted to share with you is that is the basis of how we treat cancer nowadays, and it's completely wrong, if I need to be quite frank, because we're treating it from a DNA expression standpoint. So think about all the money, all the research that's going into this, and while it's great to learn about this, it's an incorrect way of looking at cancer because there is no commonality. It's a completely random in expression of genes. So the one target, now let's switch. I spent a lot of time on why we're looking at cancer wrong. Let's look at how we should be looking at cancer correctly. So when we look at cancer from a natural standpoint, I shouldn't even say just a natural standpoint, a different context of cancer completely. These are not my thoughts. This is a forgotten about, sought after source of cancer, if you will. So originally, it's called the Warburg effect. You can look this gentleman up, Dr. Warburg. He was a scientist. It was a long time ago that he brought to the public that cancer is not a DNA expression problem, that it is a respiration problem. So let me put it like this. When you have a cancer cell and a healthy cell, one of the major things that differentiate between the two is how they respire, how they breathe. When you look at a healthy cells use oxygen. When you look at a cancer cell is also able to use oxygen, but in the presence of oxygen, it also uses a non-oxygen pathway to create energy. There's a lot more details to that. Here's a simple version of it. So when we're looking at how cancer cells breathe, yes, you can still have cancer cells that use oxygen, but they're always going to use an anaerobic effect. Let me put it to you like this. You have two cars, everything is the same except the engine. Your engine, right now that you're using, by using oxygen, is getting 32 miles to the gallon. Not bad. But when you switch to the other engine, and that's the other form of respiration that cancer is going to use, it is going to use only 2 miles to the gallon. Very, very inefficient. So that is why it's going to use a crap load of sugar in exchange. 18 times more sugar, to be exact. I mean, it varies, but 18 times more sugar than, or more fuel, if you will, than a regular cancer cell, or than a regular normal healthy cell. So when we're looking at this and we're saying, wow, cancer uses a lot of sugar, it really, really kills me that we're looking at things like when you go into your oncologist's office and they've got sugar sitting there on the desk and like, no, you need all the calories you can. Here's some Jolly Ranchers on your way out, eat ice cream. Doctors will tell you it doesn't matter what you eat, it's about calorie consumption. Well, we know that a calorie is not just a calorie. We know a calorie from a fruit is much different than a calorie from a Coke or a Pepsi, so to speak. So, I mean, that's a huge slap in the face. If anyone in your family has cancer and they're going to your oncologist office and they're saying, eat anything, you just need the calories. Because that's all they're concerned about, is you not losing weight. So let me tell you again, story of my mom. You don't die from the cancer itself. Almost never you're going to die from cancer itself. You're going to die from cachexia, meaning the wasting away, the metabolism of your body eating away at itself to stay alive. Your body is a self-mending machine. Subhanallah. Self-mending machine. Also means it's going to do whatever it needs to survive. So it's going to steal and rob itself of nutrients, minerals, nutrition to keep funding the major things in your body, your brain, your vital organs, your heart. That's why when you see patients wasting away, literally, and that you're all skin and bones at the end of their stage 4 process and they're about to die, they're not dying of the cancer. They're dying because their body's wasting away. It's going to eat up everything else in the body to try to keep the major functions and the major vital signs function properly. So that's basically it in a nutshell. So the one major target that all cancers have, as I said, if you look at the DNA version of cancer, there's many, many doors that you could enter. They try to stop DNA from replicating. They try to stop it from respiring in these certain ways. All these different drugs that are poisonous that they know. And it sucks because there's a lot of good oncologists, there's a lot of good, well-intended doctors, but they know that there's a huge, huge side effect of all the chemo that they're giving you. I'm only talking about chemo right now. I don't want to talk about the radiation. I don't want to talk about surgery. This whole talk is about chemo. So, long story short, it sucks when you have a well-intended doctor and they know that they're going to be giving you these rounds of drugs or a combination of drug therapies that they know is going to be killing the bad cells, cancer cells. The problem is these drugs cannot differentiate between good and bad cells. So what's going to happen is it's going to waste away, it's going to kill all the bad, or it's going to kill all the good simultaneously. So for example, there are certain classes of drugs, chemotherapeutic agents, that lock DNA. If you're into healthcare, I don't know how else to explain this in simple terms. You have certain base pairs at the center of your DNA, and so they handshake each other, and that's how DNA is expressed. So what they do is they handshake and take one half of the DNA. You know, DNA is two strands, if you will. So one strand, as it's being duplicated into your next cell, it's going to lock in there instead of your DNA. The drug is going to lock in there, and it's going to prevent that handshake from happening. And so you're going to kill the DNA. So that's just one type of drug class that they use. And they know that it's going to negatively affect almost all cells in the body, just the same as it's going to partially affect positively, you know. The last thing I'm going to talk about, because I'm wrapping this up, I've been going for 14 minutes already. The last thing I'm going to talk about is the fact that the only thing that we know, the FDA, USDA, the government agencies know that these drugs are very, very old in thought and in nature, and that we're doing things based off old technology. They set the bar super, super low on these drugs to be passed. So really one of the only criteria that you need to meet as a drug class is to shrink a tumor. They don't look at longevity of life. They don't look at I should say longevity of life, in comparison with quality of life. So when you look at chemotherapy only increasing your survival chances by about 3%, compare that with your quality of life. You're going to lose your hair, you're going to start losing your bowels, you're going to have no energy, people are going to have to care for you 24/7. Is that really worth it, that quality of life? So think about that. Just think about that. If you know someone who's gone through it, as I have, I'm literally making my own hair stand up on my neck and on my arms, thinking about, the things that we had to deal with my mom. And she didn't have it as bad as some people have it nowadays that I see in the hospital, so I'm very, very, very blessed. So just think about that, the quality of life versus the quantity of life, and is the chemotherapy really worth it to you? And it's hard when I know someone right now who's dealing with it. He's got a brain tumor. He just got diagnosed with half stage 3, half stage 4. He's sitting right in between, and he wants to do only natural. He said, I feel 100% confident in this natural approach. He goes in to see a quote-unquote natural oncologist. And not saying he wasn't natural, but he's sitting on a board with 6 other oncologists, and they come back and they said, the only way you're going to survive is to do 6 days a week of radiation to the brain. And now he's sitting there all fucked up in his head thinking, because he was totally on board with the natural approach. Now he's like, oh my God. And then I'm not even going to get into the other half of it, which is the spiritual and the mental half and the emotional half. So as you can see, there's a lot to talk about with cancer. This is a quick 16-minute rant, and I'm wrapping it up. So stay healthy. Let me know your thoughts. I'll get back with you guys later.